Okay, so it looks like it's about time for us to get started. So just as a reminder, this week, September the 30th, Friday, is the, oh my goodness, I can't remember, Day for Observation of Reconciliation. I can't remember the name of it, my goodness, I'm so sorry. Anyway, it's a very important observation day, so there's no classes, no academic activities, so we're not in class, and there won't be any extra work to do to make up for it. So that's Friday. Tomorrow is a problem session for Thursday's group. Monday already had it. I think that's about it. Are there any questions before we get started for today? No. Okay, so last day we talked more about interference, constructive and destructive. We introduced the idea of path difference as a way to figure out when we get constructive or destructive. And path difference is the difference between two paths. We know if waves meet crest to crest, we get constructive, crest to trough is destructive. We had to quit right in the middle of an example, so we're going to pick up today right where we left off last day. So, as a reminder, last day we had a person standing between two speakers. We called them speaker 1 and speaker 2. We know they were playing sound in phase, where in phase means that the sound comes out in the same way. They both come out on a crest or they both come out on a trough at the same point in the cycle. We know the frequency of the sound and we know the speed of sound in air, so right off the bat we could find the wavelength. And that was part A of the problem. What was the wavelength? So we did V divided by F and we found the wavelength was 2 meters. Part B was find the path difference. So what we did for finding the path difference was remember that path difference is you find the distance to each speaker and subtract them. In our picture, it shows that D1 is 4 meters. We can find D2 from our picture, even though it's not explicitly labeled. So D2 is from the person to the second speaker. We might notice that D2 plus D1 gives us the full distance of 12 meters. So D2 is 12 meters minus D1, or 12 minus 4 to give us 8 meters. So that was right where we got cut off last time. So we'll put in our D2 and our D1 and find our path difference. So 8 meters, subtract 4 meters to get 4 meters for our path difference. Part C asks, do you hear loud sound or quiet sound? So here's where we have to do an interpretation. What you may find helpful is just to have a little note where you write down what the conditions are. So I put them down on a couple of sticky notes. While you're getting used to this material, you might want to do a similar sort of thing. So my 2 sticky notes, I've got one for in phase, one for out of phase, and these are just the conditions we had last time. I even move those up here a bit. So in our problem, we're definitely talking about sound in phase because we're given in phase. If we want to sort out, do we hear loud sound or quiet sound, we have to see which condition we match. Is delta D equal to n lambda, where n is an integer, or is delta D equal to n lambda over 2, basically a half integer value? So we have to compare and we have to see. So, to do that, let me show you the method. We're going to look at our in-phase conditions. So part C, in-phase. And we're asking, for this situation, which one do we meet? So we know delta D, we know lambda. Let's see what delta D and lambda, what it tells us in this equation. So if we have in phase for constructive or loud sound, then delta D divided by lambda, which is something we can calculate, that would be equal to n, where n is 0, 1, 2, 3. So if we take our delta D and divide it by lambda, if it's an integer, we know it's constructive. If it's destructive or quiet, our comparison between delta D over lambda is n divided by 2, where n is our odd integers. So n divided by 2. So it'll be 0.5, 1.5, 2.5, and so on. So let's compare delta D and lambda, see what we get, and we'll draw our conclusion. So our example, delta D over lambda is equal to delta D is 4 meters, 4.00 meters, divided by lambda, which we found to be 2 meters, equals 2. So we see delta D over lambda equals 2. In other words, delta D equals 2 times lambda. When we look at this, we see this matches our condition for constructive interference or loud sound, where n is equal to 2. So this matches condition for constructive interference which is delta D equals n times lambda, with n equals 2, therefore you hear loud sound. So this is a pretty typical test kind of question, and this is the kind of answer I'm looking for. Compare delta D and lambda, find the result, and then write a sentence saying why this is the right answer. So you have to say it matches and say what the condition is. So kind of this is what I'm looking for in a complete answer. So then, is that part okay? Make sense? And we can put lots of different situations on this. You can get different delta D's, different lambdas, in phase, out of phase, but the process is the same regardless of what we have. Okay, for part D, I said let's repeat the problem, but let's have our sound sources out of phase. So that'll give you a little bit of practice going through the process. And I will post those answers for anybody who works on that. So now, let's take still our one-dimensional interference. So we've still got our speakers in a line, but we have a slightly different geometry this time. This time, instead of being between the speakers, we're outside the speakers. So we've got our two speakers separated by 6 meters. They're emitting sound out of phase. So the out of phase is important. A person stands 2 meters from one speaker, and they can emit varying frequencies. So this is hooked up to a sound source, and we can change the dial to change the frequency. Find the lowest frequency we can set it to that gives us loud sound, and the lowest frequency that gives us quiet sound. So let's start just by adding a little detail to our picture. So here's our observer. We've got 2 speakers. Let's call them 1 and 2. We know this is an interference problem, so we care about path length and we care about path difference. Our distance to our first speaker is this distance. Let's label that. So that's D1. Right from our picture, we can see that that's 2 meters. D2 is from our person to speaker 2. I'll draw that arrow down here. If we look at our image, we see that D2 is equal to 6 meters plus 2 meters. Okay, so right off the bat, we can look at what our 2 distances are. So part A, we want to figure out about loud sound. So let's remind ourselves what we're talking about. Loud sound means constructive interference. I'll just write CON for constructive. Let's remind ourselves about the condition. So there's my sticky note again. If I have 2 sources that are out of phase, yeah?
When the question says out of phase, does that always mean like perfectly out of phase, like exact opposites?
Yes, exactly out of phase.
Will we look at when it's like a little bit out of phase?
No. That does exist, but no, we're not going to do those. Okay, so let's look at our condition for out of phase. To get constructive interference or loud sound, we know that our path length difference, delta D, is n times lambda over 2, where n equals 1, 3, 5, and so on. Okay, really important to keep these conditions straight. This problem, we know we can figure out our delta D, so we're okay with that. We know the speed of sound. Our equation has lambda in it, but our question is asking for frequency. So at this point, let's remember that speed and frequency are related through V equals F lambda. So V equals F times lambda. That means lambda equals V divided by F. So let's put in that little bit because ultimately we're trying to find out frequency. So now we get delta D equals N times V over 2 times F. So I put in V over F for my wavelength here. Trying to find my frequency, I'm going to go ahead and rearrange this equation and solve for frequency. So my frequency is equal to N times V over 2 times delta D. So far, so good? Let's look at each of those things now that I need to put in my equation. So V is really easy, it's given. V equals 344 meters per second. Delta D is pretty easy. That's the one we can calculate. D2, take away D1. So our D2 was 8 meters. We subtract our D1 of 2 meters, and we end up with 6 meters. Okay, so far so good. So V and delta D aren't too problematic. Okay, N maybe feels like it's a little bit problematic because N is allowed to be any odd integer. Which one do we use? We have to know which one to pick. Yeah?
The lowest, because it's asking for the lowest frequency.
Right on the money there. So this problem says find the lowest frequency. If we want the lowest frequency, we have to use the lowest N value. Okay, so excellent. So N equals 1 because we want lowest frequency. Okay, so let's put our numbers in and get to our answer. So our frequency is 1 times 344 meters per second, divided by 2 times 6 meters, gives us a frequency of 28.7 hertz. Here's a little bit of an interesting question. What if that frequency turned out to be 10 hertz? Would that have been a viable answer? I'm going to go no. I see some head shakes. The reason we'd say no if we got 10 hertz, it wouldn't be the right answer, is because average humans can't hear 10 hertz. It's too low of a frequency. So if this turned out to be 10 hertz, because our path difference was the right value there, we'd have to try the next value of n. So we'd try 3 for our n instead of 1 for our n. So whenever you're talking about frequencies people hear, remember you're looking at the range between 20 hertz and 20,000 hertz, unless you're coming in with a note from your audiologist saying you can hear specifically different frequencies. So other than that, we stick in that range. Okay, so that's part A. Any questions? Part B, we want to find the lowest frequency for quiet sound. So we'll do the process again, but we'll use our condition for destructive interference. So for part B, we want quiet, which is destructive. Delta D is equal to n times lambda. Lambda is equal to V over F. So F is equal to n times V over delta D. We're going to pick n equals 1 again for our lowest frequency. Put in our numbers. 1 times 344 meters per second divided by 6 meters gives us a frequency of 57.3 hertz. Okay. So when we turn the dial to 57.3, all of a sudden the sound will go quiet. Okay, any questions? Something that I think is kind of neat about this problem, maybe it jumped out at you, maybe it didn't. The path difference was the difference between the speakers. It actually didn't matter where this person was standing. Okay. So this behavior would be true no matter where this person stood outside the speakers. Your path difference is equal to that much. Okay, that kind of covers one-dimensional interference. So all of our waves we've been talking about so far have all been waves along a line. So wave on a string, our 2D interference right there. So for one-dimensional motion, this was our equation for waves. Y was equal to A times cosine kx minus omega t plus phi. All of these values, hopefully you remember. Y was the height of the wave above equilibrium. So Y was height, A was the amplitude, K is our wave number, 2 pi over lambda. X was your position, so your distance horizontally. Omega was your angular frequency or angular velocity, 2 pi times the frequency, t is time, and phi was your phase constant. So that's the equation we've been using to describe waves. Waves aren't only one-dimensional. I would say they're kind of rarely one-dimensional. Waves are typically two-dimensional or three-dimensional. So a couple of examples would be a water wave would be a circular wave. So that just happens on the surface of the water and spreads out. But you also get three-dimensional waves like sound waves and light waves. So sound goes out from a source in all direction, 3D. Light goes out from a source like the sun in 3 dimensions. So we're still going to do our treatment of waves like this, but we have to extend it to 2 dimensions and 3 dimensions. The only difference we're going to make is that we'll still say y as a function of position and time. For our position, we'll use d. So now d stands for distance from the source. So in 1D, we specifically use x to represent distance. 2D and 3D will use d. So it's just kind of a notation change, and it follows what your book uses. If you have a different book, you might see r instead of d, but it still means distance from the source. We'll still get interference. When 2 waves meet, they can be at the same place at the same time. If you go crest to crest, it's constructive. Crest to trough, it's destructive. So let's have a look at some of those interferences. And we'll do one-dimensional first, or 2D first. So this is a video.
Where we can see this with water waves. I have 2 sources of ripples, which are basically like the 2 slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the 2 sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference, and there's basically no wave there. And this is exactly what was happening with the light.
Okay, so he goes on to talk about the 2-slit interference. If you do any optics, you'll learn all about that stuff. But you see that the water ripples, when they're crest to crest, the wave gets bigger. Crest to trough, it cancels out, and we're at the equilibrium. So we see it in 2D waves. We can also hear it in 3-dimensional waves. So we can do that here in the classroom. So I'm going to play that tone generator again, not up at the painful 10,000 hertz. I'm going to shoot for 343. Okay, 341 is close enough. Okay, so now what I want you to do is move your head a little bit. Don't go too fast. Can you hear any changes in the sound? I stopped right here where I'm standing. It's very quiet. I can't hear it very well at all. Now that I'm right here, it's really loud. I've got sound waves coming out of the speakers. The sound waves are pressure waves in the air molecules. They have crests and troughs corresponding to high and low pressure. When you put your ear at a place where crest meets trough, a compression meets a rarefaction, you don't hear very much at all. That's your quiet spot. So you're at a place of destructive interference. When you move your head to a place where compression meets compression, that's where you're getting the loud sound. So you can definitely observe this stuff in 2D and 3D. Yeah, and then if, by all means, try this at home if you have a speaker system at home, you want to impress your friends. So let's start with some examples of interference. So we get the same behavior. We're going to have the same kind of analysis, and we'll end up with the same kind of results. So let's say this is the two speakers where we just were. And let's say the sound waves are coming out, or if you prefer, you can think about it as the guide bobbing the two beach balls up and down on the water. So we have two sources. We're going to say that they're in phase, so they're happening in the same way. Two in-phase sources are emitting sound waves, so our two speakers, with equal wavelength and intensity. So the picture here is showing the two sources. I'm going to label them 1 and 2. So we've got a green wave and a blue wave. This is probably brutal for people who are colorblind. I'm sorry. I can trace it in a different color if anybody can't see it. Okay. So I've got two sources, 1 and 2. The way we draw these 2D and 3D waves is we draw lines representing the crests. So just like the water waves come out in circles, we draw these crests coming out in circles. So these lines are the crests. And that's true for the blue wave as well. In between any two crests, you would have a trough. So the trough happens between the crests. And the distance between any two crests corresponds to a wavelength. So that's an explanation of the picture. So now the question is, what kind of interference, if this was your ear right here, what would you be hearing? Would it be constructive or destructive? Would you hear loud or quiet? Oh, I can answer right away. So I heard the first answer of loud. Does anybody agree with loud? Okay, anybody disagree? Okay, anybody just no idea? How are you supposed to figure this out in the first place? Okay, so we're split about 50-50, and then the handful of people who don't want to commit, so that's fine. So let's think about what's happening at this dot right here. So let's think about the green source. Here's my source, crest and crest. That dot is in between two crests. So our dot is at a green trough because it's between two crests. And what about the blue? So here's our blue source, crest, crest, crest. It's also at a blue trough. So what we're seeing here is that it meets up crest or trough to trough. That's constructive interference. Loud sound. So there's the behavior when you think about what part of the wave you're at. That's always a good way to do a physical analysis. Our mathematical analysis with the path difference, that also applies here. So let's have a look at the path difference and our distances. So D1 is going to be our distance to speaker 1. Let's label D1 on our picture. And let's see what is D1 in terms of a wavelength. So I go from my source to my first crest. That's one wavelength. I go from that crest to the midpoint. That's to a trough. That's a half of a wavelength. So my D1 is lambda plus lambda over 2 equals 1.5 lambda. So there's my distance from source 1 to the place where I'm thinking about the interference. From source 2 to my point is from here to here. So let's think about that. I've got lambda here, and a half of a lambda here. So my D2 is lambda plus lambda over 2 equals 2.5 lambda. So there are my two distances. To find my path difference, delta D is equal to D2 minus D1 equals 2.5 lambda minus 1.5 lambda equals lambda, and we've observed constructive interference or loud sound. So this is an illustration about how our interference conditions translate. Okay, we could go through the whole process like we did last time about shifting back and forth. We'd get exactly the same answer, but it would take forever, and then we'd have to lose our chapter on magnetism. So we're not going to go through that. For people looking for a nice set of notes, I'll move this off to one side. In the class notes, I'll be posting this. In-phase waves have a path difference of delta D equals n lambda to get constructive interference. Delta D is n lambda over 2 for destructive. If we're out of phase, those conditions flip, just like the one-dimensional interference. These notes are the same as the other notes. Instead of delta X, we have delta D. Okay? So we talk about D because we're in 2 dimensions or 3 dimensions. Okay, any questions here? So the takeaway is that the conditions are the same thing. For the next little bit, your book tends to be a little bit thin on these 2-dimensional and 3-dimensional problems. So I've introduced a few examples that aren't in your textbook, but hopefully it will help you process this a bit better. So let's get going on some of those problems. So for the first, and this is a standard sort of problem that you'll see, we've got 2 speakers, 2 sources, they're emitting sound. For this specific example, I'm going to say sound in phase. So the in phase is important. I've got Susie, she's 10 meters from one speaker, 8 meters from the other speaker. So right off the bat, I'm going to label my speakers 1 and 2. I'm going to put in my distances, and I'm going to label those D1 and D2. So that's a good place to start your problems. So I'll label them speaker 1, speaker 2, distance to speaker 1 is 8 meters, distance to speaker 2 equals 10 meters. So there are my 2 distances. By default, I tend to pick D1 being smaller than D2. It doesn't matter if you take them opposite because we take the absolute value anyway. So there's our picture all labeled. We know it's in phase. Now we're asking what's the lowest frequency for which Susie hears no sound and lowest frequency for loud sound. So this is similar to our one-dimensional example we did, except now we're not in 1D anymore. So we've got our sources in phase. Rather than my sticky note, I just typed up the conditions. So I've got those here on the slide. I'm going to highlight them because that's the part of the problem we're talking about right now. The lowest frequency for no sound, that means we're talking about destructive interference. Okay. Destructive, which we typically call quiet. Okay, so we've established which part we're looking at. We want no sound, so destructive interference. Let's write down our condition. So for our sources in phase, delta D is equal to n times lambda over 2. We'll remember that V is equal to F lambda, so lambda is V over F. We care about F because the problem asks for F. So that's why I'm bringing F into this. N times V over 2F. And remind ourselves that n equals 1, 3, 5, and so on. Trying to find the frequency, so F equals n times V over 2 times delta D equals. So now we're here. Let's see what we're going to pick For our n value, we want the lowest frequency, so just like last time, we're going to pick n equals 1. Remembering that we're going to check to make sure it's audible at the end of the problem. So n equals 1 for lowest. V, let's assume, because the problem is not telling us anything, let's assume V equals 343 meters per second. Typically on a test problem, I'll remember to type that in, but if you're not certain, you can always put your hand up and ask. Typically I would remember on a test though. So our V is okay, 2 is okay, let's find our delta D next. Delta D is the difference between D2 and D1. So that's 10 meters, take away 8 meters, giving us 2 meters. So we can put our numbers in. 1 times 343 divided by 2 times 2 meters. So that lowest frequency is 85.8 hertz. And that's bigger than audible, so we're okay there. Part B, what's the frequency that's going to give us the loud sound? So we'll repeat the problem. Instead of using our condition for destructive, we'll use our condition for constructive. So loud sound means constructive interference. So our condition is delta D equals n times lambda. The lambda we'll put in V over F. Where n is 0, 1, 2, and so on. F is going to be n times V over delta D. If we want our lowest frequency, some people might argue you could put in n equals 0 and your frequency would be 0. I think I would argue if it has a frequency of 0, it's not really a sound. So I wouldn't buy n equals 0 here. We'll use n equals 1. 343 meters per second for the velocity, divided by delta D, that hasn't changed, 2 meters per second. And we get a frequency of 172 hertz. I did that one a bit quickly, but hopefully you can see it's pretty much the same as the one-dimensional example, except we have a new way to find our delta D. Okay, now let's get into some harder stuff. So we've got our 2 sound sources separated by 3 meters. Susie is standing 4 meters in front of one of the speakers. The speakers are emitting sound out of phase. So right off the bat, I'm going to highlight my conditions for out of phase interference, out of phase sources. The frequency of the sound is 688 hertz. Does she hear loud sound or does she hear no sound? Okay, so we're going to follow our process like we did with the one-dimensional interference. We know the frequency. That's telling us we can find the wavelength. We know the geometry. We'll be able to find the path difference. We'll compare path difference and wavelength, look at our conditions, and see which condition we meet. So our overall structure of this problem is the same. Got a little bit of extra work to do because of the two-dimensional nature of the problem. So why don't we start to think about our conditions first? Does she hear loud sound or no sound? So when our sources are out of phase, our condition for constructive interference is delta D equals n lambda over 2. So to get loud sound for constructive interference, we know that delta D divided by lambda is n over 2, where n is equal to 1, 3, 5, and so on. So when we compare delta D and lambda, we'll get 0.5, 1.5, 2.5, and so on. If it's quiet sound, we have destructive interference. We know that in that case, delta D is n lambda, where n is an integer. So delta D over lambda would be equal to an integer, where n is 0, 1, 2, and so on. Okay, so this sets up our process for the problem. We want to calculate delta D, calculate lambda, take the ratio, see what we have, and look at our conditions. So let's figure out delta D first. To figure out delta D, we should put those things on our picture. So D1 is the distance between Susie and speaker 1. D1 is easy, it's 4 meters. D2, here's where some people get into trouble. Okay, and I said this is where most people get into trouble with these problems. Sometimes you'll be tempted to say D2 equals 3 meters because it's the other number given in your picture. Not so fast. You've got to remember, D2 is your distance between Susie and the second speaker. So this is D2. Okay, so it's good, you should always do those drawings, label your D1, label your D2. As soon as you label D2, you recognize that you can calculate it as the hypotenuse of a right angled triangle using your Pythagorean theorem. So D2 is going to be the square root of 4 meters squared plus 3 meters squared. So D2 is going to be 5 meters. So typically in these problems, you are going to have to calculate either D1 or D2. That wouldn't be straight up given. So if we want to find our delta D, say that delta D equals D2, take away D1, equals 5 meters, subtract 4 meters, equals 1 meter. Okay, so we know our delta D. The next thing we need is our wavelength. We know lambda is V over F because V equals F lambda. V we're given as 344 meters per second. F is 688 hertz. So lambda is equal to 0.5 meters. So now we've got the ingredients for our equation. Let's figure out what delta D over lambda is equal to. So where Susie is standing, delta D over lambda equals 1 meter over lambda, which is 0.5 meters, equals 2, or delta D equals 2 lambda. So now we've got our comparison between delta D and lambda. Let's make our conclusion. So this matches our condition for destructive. Condition for destructive. Which is delta D equals n lambda, with n equals 2. Therefore, she hears quiet sound. Same process as the 1D, but a little bit more complicated because we got some more geometry layered in there. Okay, any questions? Homework problem, if we turn the frequency of sound up and down a bit, what are the next higher and lower frequencies that Susie would hear no sound? So that could be something you would try. Now I want to bring in a little bit of a conceptual idea. So same setup, but let's have Susie move around a little bit. So we've got our two sources separated by 3 meters. Initially, Susie is out here at 4 meters. Our sound is out of phase at 688, and V is 344. So in the very beginning, so this was what we had on our last slide. This is our setup. And from our last problem, we calculated that delta D was equal to 1 meter. Delta D was equal to 2 times lambda. And it was destructive interference with n equals 2. So Susie heard quiet sound. Okay, that's a recap of what we just did, looking at our conditions for destructive and constructive interference for sources out of phase. Now what happens is Susie walks inwards until she stands right in front of speaker 1. So now what's going on where Susie is standing? So she's standing at that speaker, her ear is sort of right up against speaker 1. So let's do our analysis again, and let's figure out what's happening when she's right in front of speaker 1. So an interesting thing here is Susie is right on top of the speaker. The distance between Susie and speaker 1 is 0, because she's right next to it, so no distance between her and the speaker. Distance between Susie and the second speaker is 3 meters. So our D1 is 0, and our D2 is the distance between the speakers, because she's standing right there, right at the speaker. Delta D is D2 minus D1, 3 minus 0 to give us 3 meters. So there's our delta D. Let's compare delta D and lambda to see what she hears when she's standing there. Delta D divided by lambda equals 3 meters, divided by 0.5 meters, we found that on the last slide, equals 6. Or delta D equals 6 times lambda. So when Susie walked in and she stood right next to the speaker, now the path difference is 6 times the wavelength. This matches destructive delta D equals n lambda with n equals 6. So this time she hears quiet sound again. Okay, I went through that bit really fast because it was just like we did on the last bit. Any questions? People okay with it? Here's the interesting bit, something you might notice. When Susie was far away, the path difference was 1 meter, and n was equal to 2. So out here, delta D is 1 meter, and n equals 2. When Susie walked in, the path difference is 3 meters, and n equals 6. As she walked inwards, the path difference gets bigger, the n value gets bigger. That tends to throw people for a bit of a loop. They assume if you walk right in next to speaker 1, now your path difference is 0, but that's not true. You gotta remember what path difference is and figure it out each time. If you walked farther and farther away, eventually your path difference would end up going to 0, okay? So probably important to be able to figure out or to remember that if you're getting in closer like this, your path difference is getting bigger. Okay, so, and it's going to be the biggest possible you can get when you're right in next to the speaker. So our next example talks about that, or it just takes this a little bit further. So get our same setup, 2 sources, 3 meters, Susie's at 4 meters, they're out of phase, frequency of 688. She walks forward until she gets in front of speaker 1. What did she hear as she walked? So what did it sound like? If you want to put it in context of what we just did in class, so this is just like turning the sound on the speakers. Susie has taken a walk. What did it sound like as she walked along the room with those speakers going? So when Susie was all the way out here, so right here is the initial place, D1 was equal to 4 meters. Delta D was equal to 2 times lambda. That gave loud sound. So that was our start. When we finished, D1 was equal to 0 meters. Delta D was equal to 6 lambda. And the sound, oh, I wrote loud, I meant to say quiet, I'm sorry. Quiet. And the sound was quiet again. So as she went from 2 lambda to 6 lambda, yeah.
Would she hear like a beat depending on her speed?
You wouldn't get a beat because that's 2 different frequencies, but we are going to get something alternating. So I think you're thinking the right thing, just not the quite the right word to describe it. So as she went from 2 lambda to 6 lambda, she had to pass through 3 lambda, 4 lambda, and 5 lambda. Does that make sense? So right about here, delta D equals 3 lambda, quiet. Right about here, delta D equals 2 lambda, quiet. Right about here, 2, 3, 4. Right about here, delta D equals 5 lambda, quiet. Okay, so whenever she's at these positions, she hears quiet sound. What happens in between those? As she goes from 2 lambda to 3 lambda, she passes through 2.5 lambda. So right here, delta G equals 2.5 lambda. That's a condition for constructive interference for out-of-phase sources. Here she hears loud sound. Between 3 and 4 is 3.5. Between 4 and 5 is 4.5. And between 5 and 6 is 5.5. So what Susie hears is alternating loud and quiet sounds. And ultimately she hears loud sound 1, 2, 3, 4 times. And she hears quiet 5 times. So that's what she hears as she walks. You could find those distances certainly. So for example, if you wanted to find your distance D1 here, you would call this distance D1, this distance is D2, your delta D is 5 lambda, which is D2 minus D1. That equals 5 times lambda, and you get the solve for your distance. It's a little bit of algebra. It's kind of boring for you guys to watch me work through in class. You might want to try it at home and then kind of get in touch with me if you can't figure it out. So the only other 2 slides I had for this chapter were kind of extra homework or examples for you to try. It doesn't feel very sensible to start chapter 19 when we're not going to meet again till Monday. So for today, why don't we quit a couple of minutes early, and then we'll be back with a new chapter on Monday.